Continuamos entonces con el doctor Martin Rigler, quien es científico ambiental, dedicado al desarrollo de nuevos instrumentos y técnicas para la medición de aerosoles atmosféricos en la empresa Aerosol de Ljubljana, Eslovenia. Su experiencia es en el campo de la óptica no lineal, la ingeniería óptica y los láseres UV. Recibió su título de doctorado en la Universidad de Ljubljana en el 2014, y su tesis fue galardonada con el Premio Científico Joven por la Sociedad Europea de Investigación de Materiales en el 2014. En el mismo año se incorporó a la empresa Aerosol como desarrollador principal e investigador de un nuevo analizador de carbono total y del método de alta resolución para carbono total y black carbon. Actualmente el Dr. Rigler es jefe del Departamento de Investigación y Desarrollo de Aerosol, donde es responsable de supervisar el proceso de desarrollo e investigación de nuevos productos y estudios dentro de proyectos internos, nacionales e internacionales. En diciembre del 2021, el Grupo de Investigación y Desarrollo de Aerosol, dirigido por el Dr. Rigler, recibió el Premio Nacional Puig por sus logros destacados en el campo de las mediciones de absorción de aerosoles. Hoy el Dr. Rigler expondrá sobre multiple phases of carbonaceous aerosol. Hello, Martin.
Hello. Let me just start my screen. Can you confirm that you see my screen?
Yes, we are seeing your.
Okay, perfect. Okay, thanks for the nice presentation. Thank you for the nice introduction. So today I'm going to talk a bit more general about the carbonaceous aerosol. So, you know, a bit of part of the ethalometer, which was already used in the project, and also another, let's say, instrumentation that we developed at Aerosol, which can give you much more information and the whole picture or the whole fingerprint of the carbonaceous aerosol. So this is not only my work, it's the work of many colleagues, especially the first one, Matic Ivancic, which did most of the slides, which I'm going to show. Okay, so to start with the introduction, carbonaceous aerosols, so that means all the aerosols that contains carbon atoms are extremely diverse. As you know, they impact public health, visibility, cloud nucleation, climate forcing, and air quality in general. And they're divided into black or elemental carbon and much more, you know, complex group of organic aerosol. So this is then carbon and other atoms like hydrogen, oxygen, nitrogen, and sulfur. And as we know, organic aerosol fraction is the largest one in carbonaceous aerosol and the least understood one. To clarify the terminology, so organic aerosol are the whole aerosol that contains carbon. If I'm only talking about the carbon fraction in the carbonaceous aerosol, organic aerosol, I'm talking about total carbon and organic carbon. And of course, black carbon or elemental carbon is assumed to be only carbon. Two important publications were issued last year. So the IPCC 2021 and the World Health Organization report 2021, both recognizing carbonaceous aerosol to be important one. What I, let's say, found interesting is that in all developed countries, the carbonaceous aerosol is somehow decreasing. Just in, for example, US, especially the West Coast, it's increasing due to increasing wildfires, which is also a topic that I'm going to discuss in this presentation. Okay, so of course, two phases, we have two approaches. One is light absorption, so this is a principle that the ethalometer is working on, and another is chemical refractiveness. So luckily, if the carbonaceous aerosol is more black, it's also more chemically refractive. So we have two approaches. One is using the light absorption in different wavelengths, and on the other side, quite well known and standardized method of elemental carbon and organic carbon. So it's a combination of thermal classification. So during the analysis, you increase the temperature, but due to the charring, you also need to include the transmittance or reflectance into the measurement. In, let's say, aerosol research group and development group, we are more or less dedicated to online measurement system so that you get the data in fast time resolution and in real time. And one of such instrument is, of course, a thalometer used in the project. Short principle, so you have a, let's say, filter tape inside, then you suck air through the filter, and because black carbon or elemental carbon is black, the filter spot gets darker, and then you measure. So on one side, above the filter, you have a light source, in this case with 7 different wavelengths, and below the filter, you have 2 photodiodes. One is measuring the signal, and one measuring the, let's say, white spot of the filter is the reference measurement. And because we are doing this every second, the derivative of such measurements, so the derivative of the attenuation, then gives you the attenuation parameter. So here is a simple equation, but it gets complicated because of this factor. As we all know, when the filter is becoming more and more darker, the sensitivity of the measurement, of course, goes down. And this is something that is called, the phenomenon is called loading. And you have different compensation algorithms to compensate for that. In the case of low single scattering albedo approximation, you can then convert attenuation to absorption. So this is absorption coefficient, and multiplying it by mass absorption cross section, you can get the black carbon or equivalent black carbon concentrations in mass per volume. If you do that at several wavelengths, so BC is, let's say, defined at 880 nanometers. If you do the measurement at several wavelengths, you get this absorption coefficient at different wavelengths, which you can somehow describe by this exponent with alpha being angstrom exponent. To compensate for the loading compensation, we solve this, and the solution is patent, with the dual spot system. So actually you don't measure only one spot, but you measure 2 spots at the same time with different flows. And actually then you have 2 equations, one parameter to calculate, which is the K, the loading parameter K. And actually in real time, the instrument calculates the loading and it can compensate for it. So actually the measurement with a thalometer looks something like this, while not using this, it will look something like this. So the sensitivity goes down, and when you have a fresh filter, so when you do the filter tape advance, the measurement goes up again. Okay, a bit of history, how the, you have the attenuation cross section. No, you have a attenuation parameter, how you convert to mass. This was done in 1980, and part of it was actually done in Ljubljana, at the time Yugoslavia, now Slovenia, so which we are proud of. So you have filters where you collect carbon, let's say carbonaceous aerosol or aerosols on it. Then you do socket extraction. By that you remove all the soluble, water soluble, alcohol soluble, and water non-soluble organics, so that what stays on the filter is only black carbon or elemental carbon. You measure attenuation. Then you combust everything to CO2. You have mass of CO2, mass of carbon, and the slope between those two gives you the sigma, which is mass attenuation cross section or mass absorption cross section. Okay, so this is principle of thalometer. Using different wavelengths, It can give you the estimation of sources of black carbon, so it can be traffic or biomass burning. It can give you also the estimation of brown carbon. So brown carbon is the amount of organic carbon, organic aerosol that absorbs light, especially at lower wavelengths. Now, if you include the other instrument, which is known as the total carbon analyzer, so this part here, into the equation, you get the total carbon measurement. So the principle of operation is that with the total carbon analyzer, you sample carbonaceous aerosol on the quartz fiber filter. At the end of the analysis, in the chamber, there are two heating modules which flash heat all the carbonaceous aerosol on the filter. So in few seconds, the temperature goes up to 900 degrees. All of the carbon is converted, or mostly all of the carbon is converted to CO2. You measure CO2, and then you convert back to the mass of total carbon that was collected in the filter. So you have the total carbon. If you subtract the black carbon, you get the organic carbon. This is done in high time resolution, so every 20 minutes or every, let's say, half an hour, an hour, and then you get this OC and BC data in real time and high time resolution. But it's not only OC and BC that you get out of it. So now I talk about the advanced DC minus BC method that we just developed this year. So I'll just remind you of the papers that are connected with this instrumentation. So this is, first one is paper on the ethalometer by Dinovec from 2015. And then this is my paper on the total carbon analyzer from 2020. And now the last one, this is something that I'm going to present now, is how to use both instruments to get the whole fingerprint of carbonaceous aerosol in high time resolution and in real time. Okay, so to start with the new method, I need to spend some time on the let's say basics of carbonaceous aerosols. They're divided to black carbon and organic aerosol. Black carbon is only primary. It's a product of incomplete combustion, either of fossil fuel from traffic or biomass burning for household heating or from wildfires. And then you have primary or secondary organic aerosol. So primary, again, emitted into the atmosphere by mostly incomplete combustion, but also there can be some biogenic sources as well. And therefore, the secondary organic aerosols, there are many pathways on formation of the secondary organic aerosols. These are just two, let's say, the biggest groups. So either through photooxidation or NO3 oxidation during the night. So you have the, let's say, pool of different VOCs. You need to have the oxidation, and then if the parameters are just about right, you have the equilibrium pushed from the gas phase to liquid, either solid phase, and this is how you get aerosols, secondary organic aerosols. To do a bit more of grouping of these aerosols, so BC and primary organic aerosols are primary, and these are secondary. But looking from the optical point of view, black carbon and brown carbon are light-absorbing carbonaceous aerosols, while we call it organic aerosol non-absorbing is the non-absorbing fraction. And this is also, a bit of motivation of why we want to have these fingerprints. Black carbon and organic aerosols, they have adverse health impact. BC, as small as it is, it penetrates, deepest parts of the human lungs and then goes even to the blood. And because of large specific area, it can get coated by different organic aerosols. And for example, polycyclic aromatic hydrocarbons are part of brown carbon, which they have no carcinogenic effects. Okay, So how the new algorithm looks like, I won't go into the details because I don't have time, but it measures the 6 components of the carbonaceous aerosol. So using the thalometer model, you can distinguish between 2 sources of black carbon, so biomass burning either fossil fuel. Then doing the brown carbon model, you can divide absorption absorption to black carbon and absorption to brown carbon. And using the BC tracer model, so BC tracer model is a numerical approach that looks to BC, which is of course primary, and then it looks also to organic carbon and divides it to primary with, has a good correlation with BC, and secondary organic carbon, which shouldn't have any correlation with primaries. So it's done in this way. It's been validated for quite some time now, and we can do the same, let's say, method, BC tracer method, on the absorption. And then we convert everything to organic aerosol using different parameters as, 3 parameters as OA to OC ratio and SOA to SOC ratio and so on. And the same with absorption. So here we are using different mass absorption cross section. At the end, you get fingerprint like that. And, every 20 minutes or every half an hour, you have your carbonaceous aerosol apportioned to these 6 components. So I will just quickly show 2 campaigns that where we use this. One is in California, in Southern California, with South Coast Air Quality Measurement District. This is actually the Los Angeles Basin. The one measurement station is in the central Los Angeles, one in the Riverside. So the idea is that all the winds diurnal pattern is like, so in the middle of the day, it's blowing like that, and then it's diverted by this ridge here to this side. So this is somehow a source side, and this is then the receiver side. So this is 2 years of high time resolution data for both sides, and this is then diurnal profiles per seasons. The violet one is the total carbon, and then the black carbon is the black one, of course. And you see that those lines, especially in summer, do not correlate with each other really well. And of course, this is due to secondary organic aerosol. So if we do this advanced TC minus BC method to the data, you get something like this. So again, I won't go into the details, but you see that looking at black carbon, you have this nice pattern of rush hour in the morning and the afternoon, and of course in the middle of the day, when the planet boundary layer becomes higher, everything is much more diluted and the BC goes down. But even the atmosphere being diluted, you see that in the summer you have this broad peak and vast peak of secondaries. So in this case, these are this is photooxidation, and what we get out is non-absorbing secondary organic aerosol. In the winter nights, there are these dark secondary processes, and we also get some of the secondary brown carbon. So this is here. The precursor for this is most probably catechol. So this is the VOC that comes out of biomass burning. So at the end, you get fingerprint like this. More than half of the carbonaceous aerosol in LA Basin is secondaries, around 15% is black carbon, and all the other is primary organic aerosol, mostly coming in the summer from traffic, in the winter times also from biomass burning. Similarly, we also did the campaign for monitoring the wildfires in California in these 4 years. I think the most the largest fire in California's history, or the most destructive, was the campfire event in November 2018. So this happened here near the Paradise City. And our measurement site was here in Berkeley, Bay Area near San Francisco. And this is the combination of, high-speed back trajectories, the satellite images, and also these low-cost sensors, purple air measuring PM2.5. And then you can see that part of the plume, or let's say majority of the plume, actually came across our measuring station. So this is what we measure. Again, BC and OC on high time resolution. And you can see this is, the start of the fire. Before that, a normal, let's say diurnal profile with a rush hour cycle, more or less everything, apportioned to traffic. So this is then the start of the fire and when the plume came by the monitoring station. And the second line is actually when almost 70% of all material was burned. So this is somehow the active phase of the fire, while this is more or less then the not passive but more smoldering phase of the fire. And looking at only BC and OC values before and after, BC went up for 4 times, while OC actually skyrocketed to 12 times above the value. So when looking to PM2.5 or fine particulate matter, usually the organic aerosols are the ones that are most contributing to mass, not black carbon. But black carbon, of course, because of its absorption, is more problematic for the climate forcing. Okay, so doing the advanced TC minus BC method, again, we see a lot of primaries in the active part of the fire, and then in the, let's say, smoldering part phase of the fire, we also are getting these secondaries from all the precursors that were there from the first part of the fire. And looking the brown carbon, so this is the absorption at 370. You see that the brown carbon can be a good marker for detecting wildfires or other biomass burning. So if I plot now the whole year and only the fraction of the brown carbon absorption in compared to the whole absorption, you see a nice, peaks, nice yellow points where you can see different wildfires. So this is campfire, and these are other, additional wildfires. And you see a pattern which just show you winter biomass burning for household heat. The same was done in LA, and we also detected some of wildfires. Okay, so to conclude my talk, this is presentation of our company from Slovenia, Europe. We are 35 people. I'm running the R&D from, where, let's say, we have 6 developers and 6 researchers doing different carbonaceous aerosol research topics. So with that, I would like to thank you for your attention. If there are any questions, please let me know.
Martin, thank you for your presentation. Very interesting approach for determination of organic carbon in your multiple system. No? But maybe that is important that you can explain for the public here. What is the importance that we need to determination of this difference between black carbon and organic carbon in the different aspect about, for example, climate change or the possibility to make some mitigation management. So maybe that is important that you explain for the people what is the reason that you make this differentiation from the different aerosols components. Yeah.
Okay. Yeah. Thanks for the question. So actually, you know, organic aerosols are the usually dominant fraction of fine particulate matter. So if you want to have measures that are against, you know, you want to decrease the PM 2.5, then you mean that you need to do something with organic aerosol. Of course, black carbon, but organic aerosols as well. In case of, let's say, climate changes, of course, black carbon is the second most powerful forcer for the global warming. And the same goes, you know, models usually underestimate the importance of brown carbon. So brown carbon also warms the atmosphere, especially it absorbs quite a lot in the lower wavelengths. But on the other side, the largest fraction of organic aerosols is usually the non-absorbing parts, or the non-absorbing secondary organic aerosol. And these are, you know, scattering the light. And they can actually cool the climate. So it's actually a fight between warming and cooling. So you really need to know your carbonaceous aerosol fingerprint to really either to put the right numbers in your models or to understand what's going on as the climate changes goes. And for the health effects, it's similar. I know black carbon, it's well known, danger for the general public in regarding the health effects, but also brown carbon, for example, like I mentioned, the PAHs are brown carbon actually. So it's a good, let's say, detection tool, to have different carbonaceous aerosol species, and even having it in a way what's secondary and what's primary, then you can really have your measures against different either precursors, either your sources of combustion, and so on. So yeah.